Imagine a rock sitting in a drawer, in the dark, touched by nothing. No sunlight, no flame, no battery. And yet, day after day, it silently burns an image into anything nearby, right through black paper. That rock isn't haunted. It's uranium. And in 1896, one ruined experiment revealed that atoms themselves can catch fire from the inside. This is the story of radioactivity, how a scientist's ruined experiment on a cloudy week in Paris cracked open the inside of the atom itself. How a determined young Polish scientist turned that accident into two brand new elements, and how the glow she uncovered brought her both the highest honors science can give and the disease that eventually killed her. Let's set the scene. It's early 1896, and physics has just been electrified by the most sensational discovery in a generation. A German physicist named Wilhelm Röntgen had, weeks earlier, found the mysterious ray that passed clean through human flesh and photographed the bones underneath, the X-ray. Röntgen's images caused an international sensation. The whole scientific world raced after the same question: what exactly makes an X-ray, and what else out there might make rays like it? Physicists everywhere started hunting for invisible, penetrating radiation in places nobody had thought to look before. In Paris, a physicist named Henri Becquerel had a promising hunch. Becquerel came from 3 generations of scientists who'd studied phosphorescence, the eerie way certain minerals glow after being exposed to light. He wondered, could a phosphorescent mineral, charged up by sunlight, also give off X-rays? It was a reasonable, testable idea. Becquerel had on hand a phosphorescent uranium salt that glowed ghostly green after sitting in bright light. His plan: lay the crystals on a photographic plate wrapped tight in thick black paper, set the whole thing in sunlight, and see if invisible rays fog the plate underneath. And the first test, in late February 1896, seemed to confirm it beautifully. He exposed the wrapped plate and uranium salt to sunlight, developed the plate, and there it was, a faint silhouette right through the paper. Sunlight, it seemed, was exciting the uranium salt to emit its own penetrating rays, just like Röntgen's X-rays. Becquerel was ready to keep testing the idea properly. He prepared a new batch, fresh plates, wrapped tight in black paper, uranium crystals laid on top, ready to be set out in the sun to charge all over again. All he needed now was daylight. But Paris, in the last days of February 1896, would not cooperate. The sky stayed stubbornly gray day after day of sunless overcast. With no sun to charge his crystals, Becquerel's wrapped plates had nowhere to go. So he did the only practical thing: he put the whole experiment away. He slid the wrapped plates, uranium crystals still resting on top, into a dark drawer in his desk, meaning simply to wait out the weather. It was a small, unremarkable decision, made for the most mundane of reasons. It would turn out to be one of the most consequential coin flips in the history of science. Days passed. The clouds did not break. The sealed packet sat, untouched by any light at all. Whatever Becquerel expected to find once the sun finally came out, he was, quietly and without knowing it, running an entirely different experiment, what happens near uranium, with no light involved whatsoever. By March 1st, with still no sign of sun, Becquerel decided to develop the plates anyway. Mostly, it said, out of impatience, expecting at most the faintest trace of old, leftover phosphorescence. Whatever he expected, it was not what he found. The plate was fogged, not faintly, intensely. A sharp, dark silhouette of the uranium crystals burned into the plate as strongly as if it had sat in bright sunlight for hours. Except it had spent days sealed in a drawer, in total darkness, doing nothing but sitting there. Think about what that meant. No sunlight had charged the crystals. No energy had gone in at all. And yet, energy, real, plate-fogging, penetrating energy, had poured continuously out of that rock for days, from nowhere, for no reason anyone could yet explain. Becquerel repeated the test, again and again, always in total darkness, always with the same result: fogged plates every time. Whatever this uranium salt was doing, it plainly had nothing to do with sunlight, or phosphorescence, or anything he'd originally set out to study. On March 2, 1896, he reported the strange finding to the French Academy of Sciences. Within weeks, he went further, testing plain uranium metal, never phosphorescent, never exposed to any light at all, and found it too, fogged plates continuously, indefinitely, spontaneously. The conclusion was inescapable, and genuinely strange. This had nothing to do with light going in of any kind. The uranium atom itself, entirely on its own, without being charged or fed any outside energy, was spontaneously radiating penetrating rays, apparently forever, from some hidden reserve inside the atom. And yet, almost nobody noticed. Coming right on the heels of Röntgen's spectacular X-rays, Becquerel's uranium rays looked, to most physicists, like a dim footnote to the real sensation. Becquerel himself largely moved on. The true size of what he'd found was still hiding, waiting for someone to take it seriously. That someone would be a determined young scientist hunting for a doctoral thesis topic. One most of her peers considered a dead end. Her name was Marie Curie, and she was about to make Becquerel's forgotten curiosity the obsession of her life. Marie Curie needed a thesis subject in 1897 that no one else had properly claimed. Becquerel's strange, spontaneous uranium rays fit perfectly, mostly ignored, clearly real, and utterly unexplained. She decided to measure them properly, precisely. Not just confirm that uranium fogged a plate, but find out exactly how much and why. For that, a fogged plate wouldn't do. It told you rays existed, not how strong they were. Marie needed a real instrument, and she had, close at hand, exactly the right one, an exquisitely sensitive piezoelectric quartz electrometer built years earlier by her husband Pierre Curie and his brother Jacques. The device measured tiny electric currents, and uranium's rays did something wonderfully useful. Shooting through the air, they knocked electrons off air molecules, turning ordinary air into a weak electrical conductor. Marie could place a sample in a chamber and simply measure how much current the ionized air now carried. It was a beautifully indirect but rigorous idea. More radiation means more ionized air, means more current, means a bigger electrometer reading. For the first time, how radioactive something was could be read off as an exact number, not just a yes or no smudge on a photographic plate. She tested every uranium compound she could find, the pure metal, oxides, sulfates, nitrates, every chemical combination in the cabinet. And every single one, once she accounted for how much actual uranium was inside it, gave exactly the same reading per gram of uranium. Every time. No exceptions. Plotted out, that result was one single, clean, straight line, radioactivity rising in exact, direct proportion to the quantity of uranium present and nothing else. Not the compound, not whether it was solid or dissolved, not even the temperature of the sample. Stop and feel how strange that is. Ordinary chemical properties, color, melting point, reactivity, change completely depending on how atoms are bonded together. But this new radioactivity, as she was starting to call it, didn't care about any of that. It stayed exactly, precisely proportional to the uranium atoms alone. That was the breakthrough, and it was hers alone. Radioactivity wasn't a chemical reaction, or a property of a compound, or a response to the outside world at all. It had to be coming from somewhere deep inside the individual uranium atom itself, a genuinely atomic property, the first anyone had ever found. It's worth pausing on what that meant for the atom itself. 19th century science treated the atom as a tiny, solid, unchanging ball, the final, indestructible brick of matter. Marie's result quietly implied something else entirely. The atom had an interior. Something was happening inside it. The indivisible brick had a hidden machine running within. Marie gave the phenomenon its name. In a paper that summer of 1898, Radioactivity. Rays from the atom, spontaneously, on their own. The word stuck instantly, and it's the one we still use today, well over a century later. But her electrometer had one more surprise waiting. Testing mineral ores that contain uranium, she measured pitchblende, the dark, heavy ore uranium is mined from, expecting a reading that matched its uranium content. Instead, the reading came back roughly 4 times higher than it should have. 4 times 2 radioactive. Not a small discrepancy, not measurement noise. A glaring, repeatable anomaly. If radioactivity really was a fixed atomic property of uranium, pitchblende's uranium content alone could never explain a signal that strong. Something else in the ore had to be radioactive too, something nobody had ever identified. It was a detective's clue, hiding in plain sight. Inside a lump of ore miners had dug up for decades, mostly for its uranium and a rich blue tint, prized in glassmaking. Marie's instrument was quietly saying, "There is something else in here, something rare, something intensely radioactive, and nobody has ever noticed it." She brought Pierre fully onto the project. He set aside his own crystal research to join the hunt. Together they reasoned, if an unknown element was hiding inside pitchblende, they should be able to chemically separate it out, following the trail of radioactivity itself as their only guide, like a Geiger counter decades before the Geiger counter existed. The plan was audacious in its simplicity. Dissolve the pitchblende, chemically separate it into fractions the way any chemist would, and measure which fraction was radioactive. Whichever fraction lit up the electrometer most was where the hidden element lived. Repeat, narrow, repeat. And eventually, they reasoned, isolate it completely. It worked faster than they dared hope. By July 1898, the Curies had chemically isolated a fraction of pitchblende hundreds of times more radioactive than uranium itself, proof of a genuine new element. They named it polonium, after Marie's homeland, Poland, a country partitioned off the map with no nation of its own. It was a deliberate, political act disguised as chemistry. Poland did not exist as an independent country in 1898. By naming an element after it in the pages of international scientific journals, Marie made sure her country's name would circulate the world again and again, whether the empires that had erased it liked it or not. But polonium alone didn't explain everything. Chasing the trail of radioactivity further through the pitchblende, they found a second, even more intensely radioactive hidden element. On December 26, 1898, they announced it to the French Academy of Sciences radium, from the Latin word for ray. Naming an element, though, is one thing. Proving it exists, isolating a visible, weighable, undeniable sample of pure radium is another entirely. And here the Curies ran into a brutal, unglamorous problem. Wherever radium was, it existed only as an infinitesimal trace inside enormous quantities of ordinary rock. So began 4 of the hardest years of their lives. The Austrian government, uninterested in leftover industrial waste, let them have pitchblende residue, the used-up slag from a Bohemian uranium mine. Cheaply, since once the uranium was extracted for glassmaking, nobody thought the rest was worth anything. They had almost nowhere to work. The University of Paris gave them, essentially, a derelict shed, once used for dissections, leaking rain in summer, freezing and drafty in winter, with no real ventilation for the toxic fumes their chemistry produced. A visiting German chemist later described it as looking like a cross between a stable and a potato cellar. In that shed, for 4 years, Marie did the punishing physical labor herself, stirring vats of boiling, caustic pitchblende solution with an iron rod nearly her own height, hauling and repouring heavy batches by hand, refining the same material down, fraction by fraction, toward whatever tiny trace of radium it held. It was exhausting, dangerous, unglamorous work that in freezing drafts and choking fumes by a scientist most of her male colleagues still didn't fully take seriously. There was no glory in it day to day, only endless crystallizations, endless measurements, and the electrometer's needle patiently telling her she was getting closer. And there was one eerie compensation. At night, in the dark shed, the concentrating radium fractions began to glow, a faint, pale blue-green light of their own, bright enough to read by, drifting like will-o'-the-wisps in test tubes lined up on shelves. Pierre called it their new fairyland. By 1902, after processing several tons of pitchblende residue over 4 years, essentially by hand, they finally had it 1/10 of a gram of pure radium chloride. A decigram. It sounds like nothing. It represented years of grueling labor to concentrate a substance that exists in pitchblende at a few parts per million. From that decigram, Marie determined radium's atomic weight, close to 226, proof beyond any remaining doubt that this was a genuine new chemical element, with its own fixed place on the periodic table, not some contaminated mixture or measurement artifact. The skeptics, and there had been many, ran out of arguments. That same body of work, the electrometer measurements, radioactivity as an atomic property, the discovery of 2 new elements, the isolation of radium, became Marie's doctoral thesis, defended in June 1903. It's still often called one of the most important doctoral theses in the history of physical science. The wider world, meanwhile, fell in love with radium's glow. Newspapers ran breathless stories about the mysterious new element. Entrepreneurs, with more enthusiasm than sense, started putting trace radium into tonics, toothpaste, cosmetics, and glow-in-the-dark watch dials, sold as a magical health tonic rather than the dangerous radiation it actually was. Later that same year, 1903, the Nobel Prize in Physics recognized the discovery, half to Henri Becquerel, for finding spontaneous radioactivity in the first place, the other half jointly to Pierre and Marie Curie, for proving and explaining it. Marie became the first woman ever to win a Nobel Prize in any field. It very nearly didn't happen. The Nobel Committee had initially planned to honor only Becquerel and Pierre. Marie's central role was, quietly, about to be written out of her own discovery. A sympathetic committee member, the Swedish mathematician Gustav Mittag-Leffler, tipped Pierre off in time. Pierre insisted, and her name was added. It's a small, telling detail inside an otherwise triumphant story. A reminder that even history's most celebrated woman scientist had to be actively fought for by someone else, just to be properly credited for work that was unmistakably, provably, half her own. With the Nobel Prize and international fame came real money at last and the means, finally, to leave that leaking shed behind. But fame changed nothing about the physical toll years of unshielded work had already taken, quietly, on both of their bodies, without either of them fully understanding why. Because in 1898, nobody yet understood that penetrating radiation could damage living tissue. In 1901, Henri Becquerel himself carried a small tube of radium salt borrowed from the Curies in his waistcoat pocket for about 6 hours. 10 days later, a red mark appeared on his skin, then a burn that took a month to heal. The Becquerel burn, as it became known, and Pierre Curie's own deliberate follow-up. Binding a radium sample to his own arm for 10 hours and tracking the wound for weeks, together revealed something enormous, aimed carefully, that same destructive power might treat disease. Radiotherapy had just been born, by accident, out of two men's damaged skin. Then, on April 19, 1906, disaster struck, utterly unrelated to radioactivity itself. Crossing the busy Rue Dauphine in Paris in heavy rain, Pierre Curie slipped on the wet cobblestones and fell directly into the path of a heavy horse-drawn cart. Its wheel crushed his skull. He was killed instantly, at 46 years old. It was a devastating, almost absurdly ordinary way for one of the era's greatest scientists to die, not from the exotic radiation he'd spent years studying, but a traffic accident on a wet afternoon. Marie, 38 years old, was left a widow with two young daughters and an unfinished life's work. She did not stop. Weeks later, the University of Paris offered Marie Pierre's vacant physics chair, making her the first woman ever to hold a professorship there and the first woman ever to teach at the Sorbonne. Her first lecture picked up exactly where Pierre's last one had ended. She kept building. In 1910, working with her collaborator, André-Louis de Bierne, Marie finally isolated pure metallic radium itself, not just a compound, the element in raw form, closing the loop on more than a decade of work and answering the last skeptics who still doubted radium was real. Then, in late 1911, came a second Nobel Prize, this time in chemistry, awarded solely to Marie, for the discovery of the elements radium and polonium, the isolation of radium, and the study of its properties. She became the first person in history to win Nobel Prizes in two different sciences. She remains the only one. It should have been an unambiguous triumph. Instead, the announcement landed in the middle of an ugly public scandal. French newspapers had just revealed Marie's relationship with a former student of Pierre's, the married physicist Paul Langevin, and the press, delighted, tore into her with vicious, often outright xenophobic coverage. The Swedish Nobel Committee, embarrassed, quietly suggested she skip the Stockholm ceremony entirely. Marie's answer became famous. The prize, she wrote back, was awarded for the discovery of radium and polonium, and there's no connection between her scientific work and the facts of her private life. She went to Stockholm anyway, ill and grieving, and accepted the chemistry Nobel in person, exactly as planned, a quiet, deliberate refusal to let a manufactured scandal erase a genuine scientific achievement. It's one of the clearest single acts of professional courage in the history of science. With her prize money and growing reputation, she founded the Radium Institute in Paris in 1914, a dedicated center for radioactivity research and, soon, its medical applications, training a generation of scientists, many of them women she deliberately sought out and mentored. Then World War I broke out, and Marie did something almost nobody expected of a two-time Nobel laureate. She personally designed and drove mobile X-ray units to the front lines, nicknamed Little Curies, to help battlefield surgeons locate shrapnel and bullets in wounded soldiers in real time. She personally trained around 150 women as radiological technicians, running 20 mobile units and 200 fixed stations, treating an estimated 1 million wounded soldiers over the course of the war. Becquerel's obscure uranium rays had become, within 2 decades, a tool actively saving lives on the battlefield. But all the while, radiation exposure was quietly accumulating in Marie's own body, from decades in her lab, from those wartime X-ray units, from carrying vials of radium in her pockets and keeping them, unshielded, on her shelves and even by her bedside, simply to admire their glow. Nobody, including Marie, fully grasped the danger yet. Radiation protection as we know it, lead aprons, dosimeters, exposure limits, simply didn't exist. The same rays that had made her famous, and that she now used to heal soldiers, were silently damaging her bone marrow, cell by cell, year after year. By the late 1920s, Marie's health was visibly failing. Chronic fatigue, worsening cataracts that required repeated surgery, and blood disorders her doctors struggled to explain. She kept working regardless, running the Radium Institute, mentoring students, publishing research, refusing to slow down. On July 4, 1934, Marie Curie died at a small sanatorium in the French Alps at 66 years old. The cause was aplastic anemia, a fatal collapse of her bone marrow's ability to make blood cells, almost certainly the cumulative result of decades of radiation exposure from the very elements she had discovered. The woman who discovered radioactivity was killed by it. It's one of the starkest, most poignant ironies in the entire history of science, that the substance which brought her the world's highest honors was also, slowly and invisibly, dismantling her own body the entire time. And the danger didn't end at her death. Marie Curie's laboratory notebooks from the 1890s, the very pages where she recorded her first radioactivity measurements, are still, today, measurably radioactive. Radium-226 has a half-life of 1,600 years, barely a century has passed. They've barely begun to decay. Those notebooks are kept today at France's National Library, sealed inside lead-lined boxes. Anyone wanting to examine them in person must first sign a legal waiver, then put on protective clothing before the box is even opened. Some estimates suggest they won't be safe to handle freely again until roughly the year 3500. Even her body carried the same lingering signature. When French authorities exhumed Marie and Pierre's remains in 1995 to move them to the Pantheon, France's resting place for its most honored citizens, they found both coffins had quietly been lined with lead, a precaution taken at burial that nobody had ever publicized. Marie Curie became the first woman ever entombed in the Pantheon on her own scientific merit, resting today among France's most honored dead, in a coffin that still, quietly, shields the living from what remains inside. The rock that once glowed in a Paris shed is glowing still, in its own small way, in her bones. It's tempting to tell this as a simple tragedy, brilliance punished by its own discovery. But that undersells something important, Marie Curie knew, by her final years, roughly what the risk probably was, and kept working anyway, because she believed what radioactivity could still do for the world outweighed what it was quietly doing to her. Her daughter Irene followed her directly into the field, discovering artificial radioactivity alongside her husband Frédéric Joliot-Curie in 1934, the very year her mother died, and winning her own Nobel Prize in chemistry for it in 1935. Heartbreakingly, Irene later died of leukemia too, almost certainly from the same kind of long-term exposure. Lay the whole arc out end to end, and it tells its own story. An accidental discovery in 1896, 2 new elements and 2 Nobel Prizes, and a death that same radioactivity ultimately caused. Here is that arc in full, the triumph and the toll, in one line. Let's gather what this story actually taught the world, because it runs far deeper than one dramatic discovery. First, radioactivity revealed that atoms are not the solid, unchanging, indivisible units 19th century science assumed. They have structure, they have an interior, and that interior can spontaneously release energy all on its own. Second, every radioactive element decays on its own strict, unchangeable clock, a half-life, the time it takes for exactly half of any sample to transform into something else. Radium-226 has a half-life of about 1,600 years. Wait that long, and precisely half of any radium sample you started with will have decayed away. That decay curve is one of the most dependable things in the physical universe, utterly unaffected by heat, pressure, or chemistry. Wait one more half-life, another 1,600 years, and it halves again to a quarter of the original. Wait a third, and it's an eighth. The clock never speeds up, never slows down, never stops. That unshakable regularity is exactly why radioactive decay makes such a reliable clock for scientists in completely different fields, used today to date fossils, rocks, and ancient artifacts by measuring how much of a radioactive element inside them has already decayed away. Marie's atomic property became one of science's most trusted timekeepers. Third, not all radiation is equal, and later research eventually sorted the rays into 3 distinct types, each with wildly different power to penetrate matter, a distinction that turned out to matter enormously for both safety and medicine. Alpha rays are the heaviest, and paradoxically the weakest, at penetrating. A single sheet of paper, or even the dead outer layer of your own skin, stops them completely. Beta rays are lighter and faster, punching through paper easily, but stopped by a few millimeters of aluminium foil. Gamma rays are different in kind, not particles of matter at all, but pure high-energy light, and they shrug off paper and aluminium alike. Stopping gamma rays meaningfully takes real mass, thick lead, or meters of concrete. Here are all 3 side by side, and the staggering gap between them. That single chart explains an enormous amount of practical radiation science, why a sheet of paper protects you from an alpha source, but why a lump of pitchblende in your pocket, leaking gamma rays, needs real lead shielding to be handled safely. A lesson Becquerel and Pierre Curie both learned the hard way on their own skin. Fourth, and this is really the heart of Marie's specific genius, she proved radioactivity was atomic, not chemical, through one relentless patient measurement. The same reading per gram of uranium, no matter the compound, no matter the temperature. That single straight line was the real discovery underneath the more famous ones. It's easy to remember Marie Curie for the elements she found, polonium, radium, and forget the deeper achievement was the method, rigorous, quantitative, patient measurement, applied to a phenomenon everyone else had brushed past as a curiosity. The 4x2 radioactive pitchblende was itself simply data, followed faithfully to its conclusion. Follow data patiently enough, without deciding in advance what you expect to find, and it will occasionally hand you an entirely new element. Twice. In her case, from the very same lump of ordinary-looking rock that miners had walked past for decades. And fifth, this is a genuinely sobering lesson about discovery outrunning safety. Becquerel, both Curie's and countless radium industry workers in the following decades, suffered real harm because the science of what radiation does to living tissue simply didn't exist yet when the elements themselves were found. It took years of accumulating injuries, burns, blood disorders, and eventually well-documented illness among radium workers. Before the world built the safety rules we now take for granted, shielding, dosimeters, exposure limits, the whole apparatus of radiation protection, Marie and Pierre effectively paid for that education with their own health. It's a pattern that recurs throughout the history of science. A genuine, world-changing discovery arrives well before we understand its full cost, and the earliest people to touch it pay a price nobody could have warned them about. Radioactivity gave the world extraordinary gifts and took a very real toll from the people who first held it. And the gifts were genuinely enormous. Radioactivity gave medicine, radiotherapy, still one of the primary tools for treating cancer today, using the same destructive power that harmed Becquerel and Pierre to deliberately, carefully destroy tumors instead. It gave physics the very first key to the structure of the atomic nucleus. It gave geology and archaeology a reliable clock reaching back billions of years. It gave energy production nuclear power, drawing on the same atomic interior Becquerel's fogged photographic plate first revealed. All of it traces back to one accidental result on one cloudy week in a Paris drawer. Consider the improbable chain of it. If the sky over Paris had simply stayed clear that week in February 1896, Becquerel would have run his planned experiment, gotten a clean, sensible confirmation of his sunlight and phosphorescence hypothesis, and quite possibly moved on satisfied, the deeper truth left undiscovered for who knows how much longer. Instead, cloudy weather forced an accident that turned out to be far more revealing than the intended experiment ever would have been. And a young, ferociously determined scientist, twice overlooked, first for a Nobel nomination and then by history's easy habit of crediting the men beside her, refused to let the accident go unexplained. Henri Becquerel found the spark and mostly moved on. Marie Curie built an entire scientific career, twice over, chasing exactly what that spark meant, and it cost her nearly everything in the end, except the truth she was chasing, which she got completely, unmistakably right. So the next time you see a glow-in-the-dark watch face, or hear about a cancer patient starting radiotherapy, or read that some ancient bone has been dated to 50,000 years old, remember a cloudy week in Paris in 1896, a forgotten drawer, and the woman who refused to let the mystery inside it stay unexplained. Stay curious about the accidents that turn out to matter more than the plan ever did, the cloudy sky that ruins an experiment and, in doing so, reveals something nobody was even looking for. Some of science's biggest doors have been opened, entirely by chance, by the weather simply refusing to cooperate. If this story stuck with you, do two quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments, which part of this surprised you the most? I read every single one. So keep exploring. Your next story is just one click away. I'll see you there.